Okay, we are starting our next session, and we have here a very distinguished professor who has become very distinguished in a very short time because he has published very significant results. And he was very much noticed by the wider research community. Professor Christian Breyer is professor for solar economy at Lund University, Finland. His major expertise is research in technological and economic characteristics of renewable energy systems, specializing for highly renewable energy systems and on local but also global scale. Research includes integrated sector analysis with power, heat, transport, desalination, industry, and power to X, technologies that are coming. He previously worked for Rainer Lemoine Institute in Berlin and for Q-Cells. He is a member of so many committees that it would take a few minutes to list them all. I think it's better if we ask him to come here and take the floor. Christian, the floor is yours.
Thanks a lot for the kind introduction. And it's a great pleasure and honor to talk today on 100% renewables in the place in a conference where this topic is standard topic since many, many years and much earlier than in most other communities. So that's really great. And then I asked myself what should be the special spin of the presentation, and I wanted to focus what is the impact on primary and final energy demand, because this we see here and there in the papers, but it's not so much focused. Please forgive me, I have maybe in the end only 5-6 slides where I really go on this topic, but this summarizes then many of the other slides. So first of all, why this is so important that we talk on sustainable energy systems, and then if we talk on sustainable energy systems, they have to be in the very end, by definition, renewable ones. And you see it quite well from the 1.5-degree report from IPCC from last autumn, that by 2050 we need to have a net zero emission system. And I guess most in the room we already knew that before. But maybe for many is the most depressing insight, and beyond it has to be net negative. And the more we get in delay with really scaling down CO2 greenhouse gas emissions now, the more negative it has to be. Just take this trajectory, this P4. This means we have a lot of inaction, what is currently practice in the world, and then a late but steep decline of greenhouse gas emissions, most likely due to dramatic failures of ecosystems, social systems all around the world. Then we have to go to massive negative emissions. And even if we would know technically how to do that, I guess we all would have some ideas, I would have no idea how to get that ever financed in a fair way. Okay, so the challenge is brutal. Why we talk on CO2? I think this is a no-brainer that around 80% is CO2. Then we have methane and other greenhouse gases. The majority comes from the energy system. Then we have land use issues. Unfortunately, most of this is still for the stupidness that we destroy forests. We crop them down, we burn them down all over the world. And if it's not done in the countries where we live, then very often with our lifestyle we contribute to that. That has to be stopped immediately. Then we have agricultural emissions, and they will be outstanding complicated to get them down, because we talk on cattle farming, we talk on rice, such kind of things. And that belongs to us since thousands of years of our culture. So I would doubt that we will be fast here. The consequence for the energy system is everything what can be technical brought to zero has to be done. Because to be net negative, we have already to fix, and in particular the agricultural sector, so there is no excuse in the energy system. All fossil molecule in 2050 which still remains in the energy system is a failure. That will be the consequence of that. Luckily, more and more get this point. I was very happy to see this news. It was spring this year that several European member states call European Commission, please provide us better scenarios. because in the last autumn we got a lot of nice European Commission scenarios. Even net zero emission scenarios have been there, but not a single 100% renewable scenario. And this violates the policy of several European member states, where it's the clear dedicated policy target to go for 100% renewables. So that's good news. We already saw the picture of Greta Thunberg today. And please remember what we have observed just a few days ago. This was for September 20th, where have been the climate demonstrations, school strikes all over the world. In this one single week, where this had been the peak of this demonstration so far, there have been 7 million people. Most of them are even not yet allowed to vote on the streets globally, on all continents, in all cities, in several countries, in several cities in the world. It had been the by far largest demonstration to any topic ever in their history that we should take serious. So hopefully in a few years we can talk, this had been the societal tipping point, hopefully. It was already mentioned that not everyone has the idea that kids should fight for their future. Luckily, Scientists for Future in several countries in the world, we have nowadays even a science paper on that from different scientists in the world supporting it. This is just another paper from the German-speaking scientists. So it's really important that we have this very strong alliance, that the youth of the world do really what they have been taught in school, rely and trust in facts. And this finally, of course, one can find in science. And maybe this is nowadays, unfortunately, a news in policy, but it's important that we go back to science and facts. Now let's come a bit more to the inner core of our topic. So if we want to have a fully sustainable energy system, then the first and most important question is, do we have all the resources for what we need? And this is the diagram I really like most. It's from Paris and Paris. Just to have a rough indication what might be our energy demand. This should be primary energy demand now and in 2050. And then compare this to the resources, to the conventional, what we have as of today, and then to the more sustainable or sustainable renewable ones. And what we find immediately is wind could do it alone, solar could do it alone, and the rest can support and complement. Of course, in different countries in the world, different resources have a different resource strengths. So maybe if a smaller country lives on a volcano, then maybe practically everything can be done with geothermal energy. But on a global scale, solar will be very important, and in many regions in the world, wind, but also hydropower will be very important. And for bioenergy, we have to be very careful that we do it in a sustainable way, but there are many of these options, and then it's a super valuable source. I've done kind of an overview on the 4 most relevant technologies, at least from our research results. Solar photovoltaics, so this is the resource map in the world. We can access it all over the world. It can be used on buildings in well-developed countries, in buildings where people still have the development ahead. By the way, this is the PV system here. Photovoltaic power plants, and the good news is this is now in most places in the world the least cost source of electricity. This is the good news number 1. The maybe even better news number 2 is most PV modules currently have an efficiency of around 20%, but the physical limit is 80%. So a lot of progress will be ahead, and I guess from a scientific point of view, the road is now more or less open to 30% efficient modules. Maybe with silicon perovskite tandems, so they're now, I think, close to be industrially introduced. So there we have really good chances to get it even lower in cost, even broader applicable, and this all over the world. The most important number, by the way, on this diagram is the number you cannot see directly. It's a factor of 2. So in the moderate regions, so I'm from Finland, so go here to the moderate regions in the subarctic, and then take the very sunny regions in the world, is a factor of 2 of solar irradiation. It's only a factor of 2. So that means if it costs 2 euro cents or 20 euro cents a kilowatt hour or 20 euros a megawatt hour to produce solar electricity in the Sunbelt, then it costs in the subarctic 40 euros a megawatt hour. And this is the most important message. And it will further decline. Wind energy, we know it's accessible all over the world, in all major regions, but not in every single spot. So if there is a rainforest region, then typically wind energy is not that perfect. If it's in the very north or in the very south, then due to the conditions on our planet, wind is excellent. We know the best spot in the world is Patagonia here, but in the northern hemisphere we should not complain too much. It can be nicely built in forests. Here this is a semi-offshore. It's in Finland, between Finland and Sweden, in Åland. It's in offshore conditions, but built on rocks. So all different options are possible, and it's very, very valuable. Then a most important further component, batteries and electric vehicles. So as a stationary battery in buildings, this is Tesla Model 3, what we can even enjoy here, so that's really great. And we see steep growth rates for electric vehicles in the recent years, between 50 and 70%, and this is exactly what we need. This is also driven by cost decline of the battery cost, and in the end this will be very beneficial for both of these products, but of course we will see it in more. Of course we have all electric buses, and scientific, leading metropolitan areas in the world like Shenzhen, there is since 2 years are all 17,000 buses all electric. And then look to several of our European cities where it's now started the debate. That's really a shame from my point of view. We have to be much faster. And then the fourth most relevant technology, and this is then for the really complicated, or it's more a bunch of technologies, for the most complicated and really hard to abate segments of the energy system is all what we call power to X. If the starting point of research started in the fossil world, then we typically call it CCU, but in the end it's typically the same, whether we have carbon capture and utilization or power to something. From a specific point onwards, we all talk on the same topics. The idea here is that we have sustainable electricity, then we go to hydrogen, where we need then water. If we want to go to hydrocarbons, then we need the CO2 from somewhere. If we have a sustainable CO2 source, and some of them exist, or a not avoidable CO2 source, just think on the limestone part of cement mills, very, very, very difficult to substitute. Then we have waste incinerators for municipal solid waste. There will be always something remaining. And then, for example, pulp and paper mills, sewage treatment plants. So we have some sources, point sources of CO2 we can use very well. And the rest we can take from the air, as this indicates with CO2 direct air capture. And then we get the entire world of hydrocarbons. So we have to start with CO2 or carbon monoxide here. With hydrogen we have the syngas. Then we can go to methanol, to olefins, we can go to Fischer-Tropsch with diesel, naphtha, whatever we want. Or, of course, with hydrogen, and again from air, but then it's nitrogen from the air. We can go to ammonia, we can use it as a fuel, we can use it for fertilizers. And only the ammonia industry, as of today, where the hydrogen comes from fossil steam methane reforming, produces 1% of all our greenhouse gases. And the entire chemical industry, 5%. So there is a lot to be taken. Now it's the question, there is a very strong rationale for electrification, and this is in the end efficiency. And this brings me already close to the core topic of this talk. Let's start with electricity. So what is the main segment as of today where we get electricity from? It's typically thermal power plants. 40% efficiency, by the way, is already optimistic. In the latest World Energy Outlook, you find that the average of all thermal power plants in the world, average efficiency is 35%. So the consequence in the real world is the primary product of these plants are clouds and warm water for fish when it's cooled down. In other words, the second law of thermodynamics is not our friend when it comes to efficiency. So this is the cause of it. When we compare that to renewables, then we have very, very high efficiencies. And here I have to explain how we define primary energy. Primary energy, at least in most definitions, it's done when we extract energy for the very first time from environment, then we define it as primary energy. The consequence is that crude oil produced or a gas in a gas field or coal in a coal mine, this is then defined as primary energy. The same when we crop down a tree, from this moment on it's primary energy. However, it's the same when we have a water flow through a turbine, then we have primary energy, but then it's now electricity. It's the very first time that we extract it from the environment. And of course, the same is true when we have a wind turbine where we have the wind flow, then it's converted directly to electricity, or the same with a photovoltaic system. Due to that, this is the right comparison of efficiency when we have the first step of primary energy. We can compare that to heat. If we have very efficient heat systems, then we can be maybe even up close to 100%. We know such solutions, they're really great. However, if we have heat demand for space heating and we do it with heat pumps, then we can have an efficiency of 300 to 400%, in particular when we start with renewable electricity here. So again, there's a factor of 3 in between where we can lift the efficiency. This has a strong impact on the overall efficiency of energy systems. Let's do the final comparison here for the transport sector. 25 to 40%. Again, this is a bit optimistic. The average efficiency from well to wheel for our combustion cars is 20% or less. So this is finally a heating on wheels. And it rolls as well. 40% I think is true when we talk on marine applications, aviation applications, there it should be around 40%. But this is the range, and the rest again is losses. If we have the comparison to an electric vehicle, then the efficiency, systemic efficiency can be on the level 70 to 80%. Again, enormous boost in efficiency. Okay, so let's have a preliminary insight for the energy transition to very high shares of renewables. Then first of all, the increase of efficiency is the substitution of thermal power plants with renewable electricity, the introduction of heat pumps, substitution of combustion road vehicles with battery electric solutions. By the way, thermal desalination with reverse osmosis is the same. There we have the highest efficiency gain. We talk on a factor of 4T. So this is really outstanding. But there is a phase change in between that makes the difference. However, we have also other factors, and this makes it a bit more doubtful. And of course, the opponents of highly renewable solutions, they always point on these items, and of course that we have to investigate more. The curtailment of renewable electricity generation is a loss of energy without any doubt. We have storage losses for power, for heat, daily buffers, seasonal balancing. We have synthetic fuels of all kinds what we need if we want to remove all fossil fuels from industrial and energetic use, synthetic chemicals, and much of the power to X chain is related to some losses. And now the key question is, are the efficiency gains higher than the additional losses? Good question. It took me the last 10 years to get a bit closer to that, and I would like to share some of the insights. First of all, a quick overview on 100% renewables. So we have now more than 50 countries committing to that, and I think it was a really tipping point when California switched last year. Then it became everything much more serious, and the opponents much more, how to say, put down their volume. We have it with cities. Several countries are already there, by the way, and more companies committing to the target, which is really good. And I'm very happy that Henrik Lund is just sitting here. We did this paper together where we did a kind of a first overview where in the world 100% renewable energy systems are studied. And we have to conclude that in Europe we understand it quite well. In Australia it's very well understood. In the US is a super good leading team. What the rest universities do on the topic, I still question myself. But for the other regions in the world, it's not yet well understood. So much more emphasis has to be taken there. And what's important, of course, we see a growing trend, in particular for the last 10 years, that there are increasing numbers of papers, and also more and more of the papers really focus the total energy system, what we then call a smart energy system. And these are all key diagrams why there will be a super massive change in the system. This you already saw. We have enormous pressure to get our greenhouse gases fixed. However, this is the reason why we have to move very fast, or at least one of the major, if not the major reason. But this are then diagrams from the solution space, how we get it fixed. So here you see the cost regression or the projection of that from photovoltaic systems, photovoltaic power plants. In several places in the world, you can build nowadays a photovoltaic power plant for 500 euros per kilowatt peak. And due to the learning curve, it continues to go down. We see similar trends with utility scale battery systems. This is a cost projection, a very rough cost projection for electrolyzers, which is super important because we need hydrogen at all different corners in the energy system. And the more low capex the electrolyzers are, the more they can be run. Technically they can be run, but economically the more they can be run in a flexible way that they go for load following of photovoltaic and wind. And this is CO2 direct air capture, where the cost can go down with respective scaling of demand. So these are all standard experience curves and learning curves. And this brings the solutions down very fast in a very economic manner. This is the study we published on the power sector, and we called the paper Radical Transformation, based finally on evolutionary steps. Radically means this is more or less our present system globally for power generation, coal, gas, as the dominating forms. And when we got this result for the very first time, even as with a, how to say, background in photovoltaic industry, I was shocked by this high share of solar photovoltaics. And for several months, I didn't believe the result, and we did several, up to 20 model improvements. The only what changed was 70% to 69%. And then I started to accept the result. Of course, why solar energy, solar electricity in the power sector would have such a very high share? First of all, it's the least cost source of electricity, reason number one. Number two, cost of batteries go down very fast. Then the day-night cycle can be simply overcome. And the far large majority of people in the world live in the sun belt, and there solar energy is available like a clockwork throughout the year. These are the key reasons. And then you see that the system levelized cost of electricity steadily go down, but in an evolutionary way. So in 5 years time steps to time steps, you see it changes gradually, but in the end we end up in a different system. I have to be very honest, it's a 99.7% renewable system. We accepted that existing nuclear runs to the end of the technical lifetime, so there are a few reactors left. The cost-wise, the system is dominated on solar, plus batteries, plus wind energy, but you see a long list of different components. Now I would like to give you an overview on the overall energy system. There's practically all included, with a few exceptions I will point out to that. So it's currently, when it comes to the SDEWES spatial resolution, the largest or the highest resolved global model which exists. We have 145 regions, and the second most resolved has half of that regions, and it's done by Sven Teske and the German Aerospace Center together. They also published it this year. And the standard global models, what we have, they use 20 regions. 20 regions means one region for Europe, and then from this beautiful city up to far north in Finland, where I am, everything should be more or less identical. This is, of course, obviously nonsense. So due to that, we have to go to higher resolution, and this all over the world. And the model is run on full hourly resolution. We discussed very long whether we should have also time slices, as many of the models, or full hourly resolution. And then we thought, okay, no compromise, all hours in the year, because then you can ask me, here in Ethiopia in the year 2035, in autumn, how does it work? And then we can deliver something. Okay, everything is based on assumptions, as all these models are based on assumptions, but at least there we can make sure that all hours of a year based on these assumptions run well. What I show you now is based on roughly 100 technologies. We have done it in the meantime in a bit more detailed, but it's not yet included there. This is all available in report, as a report with the Energy Watch Group. You find it there on the website. And now, what is the outcome for the total primary energy demand? And here you see, first of all, this is now the entire energy system. Again, there is coal, there is gas, but then of course much more oil, which has mainly to do with the transport sector. But the solution seems to be very similar. Then I was again very surprised why we know already this, these shares from the power sector, and the solution is rather simple. Or the explanation is rather simple, because in the very end this energy system is practically fully based on electricity, at least to 90%, and then we should be not so surprised that we find the structure again we found earlier for the power sector. What does it mean for electricity generation? Here you can see we have this year maybe around 28,000 terawatt hours of electricity demand generation, and that will go up far beyond 100,000 terawatt hours. But of course the reason is that practically the entire energy system shifts toward electricity, and the reason is in the very end that here we find the sustainable solutions in an affordable way. For the heat generation, there is then still a lot of bioenergy there, of course. But then a lot of heat which comes via power to heat, whether directly with electric heating. Just imagine when we have to go for very high temperatures, then it's still the question, can we do it all electric, or whether we have to burn something. We had to be a bit more conservative there, having also burning elements there. But of course for space heating we can have a lot of heat pumps, what you can see here as well. What does it mean now for the energy system cost? Because we all know the creation of such scenarios might be not so complicated. We do it by definition, but in the end it's always the question of society how to pay for it. And I guess here the message, it's really different, because the message is, yes, we can go for a transition, and I will show you in some slides later. We talk on a 1.5 degree scenario in the very end. But the transition can be in a cost-neutral way, if we do it in an optimized way. And this is, of course, in strong contradiction to what we typically hear from 1.5 degrees Celsius scenarios, and I will come to that back in my very last slide. The question is then, do we need some storage? Yes, of course, we need quite a lot of storage, as you can see here. So storage output for electricity sector, for heat sector. The good news is, if the cost of batteries go down as we saw in the last decade and as it's projected to continue, then we have the perfect basis for a most efficient storage. First of all, we can use them for a long enough period. We can, in principle, recycle them, and the efficiency is high. So that's all very, very good. As a consequence, a lot of batteries are found in the solution. When it comes to heat, then it's high temperature heat storage, district heating, of course, and gas. Gases, we modeled it to be on the safe side with methane, but I guess in the next update there will be not any more much methane, and the reason is we don't trust that the leakage is zero. But whenever you have a leakage in the methane system, then you have one methane molecule with a factor of 100 more global warming potential in the next 10 to 20 years compared to a CO2 molecule. And since the fact we are close to the major tipping points in the world, it's not acceptable. So we have to be very careful when it comes to methane. if there are better solutions, of course. Transport sector, this is important to explain you. We are super conservative from the other side in that scenario. And super conservative means there is a factor of 3 assumption for more transport kilometer and passenger kilometers from 2050 to 2015 to 2050. So a factor of 3 in more energy services. This is based on respective international references from IPCC or International Aviation Association or Marine organization, so should be there on safe ground. But this is in strong contradiction to most global 100% renewable scenarios. Most assumption there is we will not travel anymore much. And I don't trust in that. Because I know all us, and that we send the goods all around, so better be on the safe side. If we need less of the services, perfect, but better to be conservative, to have a higher assumption. That's here, for example, the assumption of cars is the current car stock in the world is 1.2 billion cars, which grows by 100 million cars a year, and we have the assumption to stabilize, hopefully, around 2.5 billion cars, or 3, but somewhere in that order. But this would already assume that, for example, a region like Europe, we all together have per capita less cars. Hopefully this trend will happen. But the good news is, if we then factor this through our model, then we find that despite the factor of 3 and more services, the final energy demand stays more or less stable. And this is, of course, quite remarkable. But the key reason is, and you can see it here, currently 80% of all energy demand is due to vehicles on roads. But if we switch there from combustion cars to all electric cars, then the demand goes down, even if we have a steep increase in further energy services. So this is really great news. And you can see it here. So this is then, and here you see the level of depth, how we do it. So we have light-duty vehicles, these are the cars, then we have bus, then we have 2- and 3-wheelers, which is most important in Asia. Then we have the delivery trucks like DHL cars, UPS cars, and then heavy-duty vehicles, and these are all for battery electric, fuel cell, the combustion cars, and plug-in hybrids, and this in the full resolution with assumptions. And there you can see that even with a strong increase in demand, the total final energy demand for road goes down. It's not so lucky when we talk on marine, what you can see here, or aviation, what you can see here. Here really a factor of 3 in more demand really translates to more final energy demand. And this, of course, from a primary energy point of view, hurts even more if we go to power to fuels. And this you can see here. And this is, maybe I focus on this diagram here. This was also kind of a shock for me when I saw it the very first time. When you regard the full transport sector, and please do that, we have several models where the transport sector is modeled, but only for the road segment. But the road segment might be hard to believe, but still the easygoing part. What is really, really hard is marine and aviation, because there we have either huge volumes of biofuels we may not have, or we have to do it with power to fuels. But other sustainable options we don't have, except we go for the degrowth option, and then we do not send goods and people anymore around. But it's complicated to find a good solution. What you see here for the transport sector, to get it finally practically electrified, we talk on the same electricity demand in 2050 as of the power sector in its structure as of today with further growth. So 50,000 terawatt hours, roughly a factor of 2 of today's power sector. However, only a third of that, you can see it here better as a third, is due to direct electrification. And we are here really at the limits. Direct electrification when it comes to train, short distance shipping, we have assumed direct electric. We know there is policy target in Norway in 2040 to have all flights with 500 kilometers around Oslo all electric. And there are currently a lot of development startups and companies developing all electric flights with up to 100, 150 passengers. But the point is most of the flights are intercontinental. So in the very end we have roughly a third with direct electricity, and then is the question how to do the rest. And it could be with hydrogen, liquefied hydrogen would be my personal best bet to go for liquefied hydrogen. Then we can have LNG, so liquefied natural gas, but of course it can be power to gas, then it's renewable. And then we can have it in a liquefied way. It could be, by the way, also biomethane and then liquefied, and this might be a good option for ships. Or then Fischer-Tropsch fuels, which are assumed here. Direct air capture would be also needed. I already showed this diagram before. From the process we need electricity, but the main demand is heat. And the main heat demand could come then from also heat pumps, because luckily most of the processes require heat between 70 to 100 degrees Celsius. So it's well accessible with heat. Oops. So it should work now again, sorry. So we should have good chances with heat pumps, and then we can extract CO2 from the air. If you look into the literature, then typically you find very high cost points based on a technique which requires very high temperature. At least these are most of the publications. And for the low temperature route, there is a minor share of the publications, but practically all startups or companies in the world developing this technology on the low temperature route for good reasons. If you then model it of the low temperature route, and luckily we have now several publications on that, it's doable, well doable, that around 2050 in practically all relevant regions in the world, one gets it around 50 euros per ton. And then it makes sense for all power to X. If there is waste heat available, then it can go down to, let's say, 35 euros per ton. And then it's quite interesting. Okay. I think I already showed that. What's important, what does it mean then for the greenhouse gas emissions? So for the sectors power, heat and transport, we can go down to 0 by 2050 without negative emission requirement. That's important, and if you add up then all the greenhouse gas emissions, then it would be around 400 gigatons, which is then 1.5 degrees Celsius scenario. Here you see the power sector is the easiest part. Heat sector is more challenging, in particular for high temperature heat demand, and transport sector is currently, as of today, 97% fossil. So there is even not yet really well started the transition, except some electric vehicles. So we cannot avoid to further increase, but then we need a steep decrease, and in principle it's possible. When we have then a look on a regional variation, then again you can see most regions in the world would be based on solar energy, but there are regions with excellent wind access where wind turbines, it would be a wind-based system. So based means more than 50% or at least 50% of all primary energy from the source. Still some hydropower here and there, and then we have some regions with a technology mix which is typically wind and solar. Maybe 1, 2, 3 words when this global results are compared to the 2 other teams with several publications in the field, with Mark Jacobson from Stanford and Sven Teske in the German Aerospace Center. Then you find in principle we all come to the same conclusion: one can do it. There is a different assumption of how much combustion should be in the process, and then you see the difference from primary to final energy. You see, we assume the highest final energy demand, but have still the lowest cost. And the reason is we have the highest solar photovoltaic share, which drastically drives down the cost if you assume cost as of today and how they develop. And then the deviation is what is the assumption in wind energy and what is the assumption in solar energy or biomass. For example, Mark Jacobson blocks biomass fully in his models due to air pollution reasons. When we compare that for the transport sector, so our results are in the first line, and this is then compared to, let's say, the sustainable community. Here you see the fossil share of the total final energy demand in 2050 around 0. Then many of them have a really low total final energy demand, and I'm not sure whether we can be so efficient and so less traveling. But this is the assumption there. And then we have the more, how to say, the conventional group. And there you find very high shares of fossil fuels, and this practically cannot have to do anything with a 1.5 degrees Celsius scenario, so they do not fulfill the ambitious targets of the Paris Agreement. However, there are differences. So just compare the most ambitious Shell scenario to the other fossil guys. Then you see they have noticed there is something happening on the road with electric vehicles, and even synthetic fuels exist. For BP and Exxon, this is still something what is new. I was really surprised when I compared then our synfuel share in the total final energy demand. There we have the highest of all others. But the reason is we do not bet on energy crops. So in our model there are no energy crops. It's only byproducts, residues and waste from bioenergy for sustainable reasons. Okay, so we agree again there is no consensus. Maybe we have expected that. I switched that due to the fast running time, and I would like to give you a kind of an overview on what efficiencies we roughly talk on when we come to power to X processes. So this is, we start with renewable electricity, we go to hydrogen, to synthetic natural gas, then it's assumed it's shipped around the planet. So for liquefaction, then shipping, regasification, and then I guess we have SNG, so the centers of excellence, renewable electricity resources could be decoupled from the centers of demand. And this, let's take this rule of thumb, overall efficiency 50 to 60%. This is similar, but now it's a Fischer-Tropsch process. So we start with renewable electricity, go to hydrogen, then to syngas, where CO2 has to come from somewhere. This is assumed from direct air capture. Then we have syncrude, hydrocrackers. Again, we have then jet fuel and diesel. It can be adjusted in different ratios. Naphtha can be used for the chemical industry. Again, the efficiency is around 50%, maybe a bit more, but around 50%. This can be done then for power to methanol, power to dimethyl ether, which can be used as a fuel, but also a very valuable bulk chemical for chemical industry. Again, it starts with renewable electricity, goes through the process. Again, we have methanol and dimethyl ether, and again, 50 to 60% efficiency. The same can be done with power to ammonia, renewable electricity, hydrogen, air separation unit, where finally the nitrogen comes from. Then we have the ammonia synthesis. Again, we have ammonia, which can be used as a bulk chemical, but again as a fuel, so it can be also burned. And then efficiency even higher. So, but again, more than 50, maybe even more than 60%. Summing up, we did this once and compared it roughly. What is the range of fossil fuels with cost assumptions for the year 2030 with a cost of capital of 7%, which in specific constraints should work. And then one says this starts to be in the range that it makes sense. So now assume a CO2 price of 50 euros per ton, so CO2 price for fossil emissions or higher, plus fast declining cost of renewables, renewable electricity and scaling, then this power to X options are really in scale. That's very important. Now let's sum up. So various losses in the renewable in the 100% system are there. Luckily, and these are now mainly the results we found in the last few years, electricity storage losses are surprisingly low. And the reason is that only, let's say, roughly 1/3 of the generation has to be stored, and the rest can be used directly if we have overall optimized systems. Overall optimized means we have a generation portfolio, solar, wind, hydro, biomass, and we use them when they're really needed or available in an optimized way. Batteries can store most of the electricity as the least cost storage for electricity, so we regularly find 90%, and they're at high efficiency, so we don't have much storage losses. Seasonal storage can be at a negligible loss, and this was a major surprise for me because I started with that research 10 years ago, and there we had huge losses there, but the reason was a not well adjusted energy system. But then in the latest simulations what we have, we only need power to gas to power for 0.3% of the total electricity demand, and the rest can be captured by other flexibility options, in particular hydro reservoirs, biomethane, and other options. The curtailment is also surprisingly low, so we find now values below 5%, but you have to be a sector-coupled system, and a very flexible one. And we find a lot of papers where they even have 30, 40, 50% of curtailment. If you see such a paper as a ref here rejected, it's for sure wrong. So all values above 10% have to be checked in much detail, whether it's really okay and whether it's the cost optimum. But for sure more than 20% cannot be true. Power to fuels efficiency is about 50 to 60%. So already mentioned it before. However, it can help also to drastically reduce the curtailment, and the reason are flexible electrolyzers. You saw hydrogen everywhere, but if you have low-cost electrolyzers, then they can follow PV and wind, and that makes it really valuable. Flexibility, of course, supports the loss reduction. Electrolyzers I already mentioned. Thermal energy storage delivers flexibility that we see then in district heating and other solutions. In addition, with heat pumps, they can follow the availability, and also this can reduce curtailment. And of course, smart charging of battery electric vehicles is a very valuable source, vehicle to grid as well, of course. Due to time, I would like to skip this and now come back to the core of the entire talk. So what does it mean in the long term? So this is when we aggregate power, heat, and transport. By the way, industrial demand is used for power, heat, and transport as well. The only what is missing there is chemical industry with the non-fossil demand. With the non-energetic demand. That's not yet there and would be roughly 10,000 terawatt hours more. But here you can see, first of all, there can be a drop of primary energy demand while final energy still increases. And the reason is that we can get rid of thermal power plants or not so efficient heat solutions and on the road segment. But then again, we need more electricity to the overall energy demand grows, the population grows, and more power to X demand. To the other diagram I will come. And here you see the comparison is the same diagram as on the other slide from the total primary energy demand. Here you see the total final energy demand, which is continuously growing. And this is then supporting that the energy services can even grow faster with more efficient end-use technologies, but still we need then a growing total final energy demand. But we can improve much, much more in the primary energy demand. And you can see it here, so the same shape as of here is here used for the total primary energy demand. And if we would apply the efficiency as of today for the 2050 total final energy demand, then the primary energy demand will be twice as high. And this is the key advantage of going to 100% renewables from an efficiency point of view. We get a much more efficient energy system, and the reason is we go much more for electricity. And you see it here, this is the primary energy demand, again the same shape as here, but now in the fuels. So with electricity, heat, and the fuel demand. And you see in the end, it's from the primary energy point of view, 90% electricity. If you go from the final energy point of view, you don't see it, because there is of course still a lot of fuel demand in the marine and the aviation, for example. There's a lot of heat demand for industrial process heat, but also for space heating demand, but it started with electricity before. So we have to be very careful when we report on the share of electricity, whether we talk on final energy or primary energy. That really makes a difference. This is now my final slide. And this is why I'm nowadays, for the last 10 years, several of you will know me that I'm a critiker of International Energy Agency. It has not changed much, but now I'm really worried about IPCC. And the reason is this is a much more valuable and relevant institution nowadays than IEA. And our international climate policy is based finally on IPCC reports, and whether we as a civilization fail or not is finally in the very end traced back what we get recommendations there. And then I'm now really worried that as scientists you have to be very careful when you say this, but I would assume that the major conclusions of the IPCC reports to be still positive, strongly distorted. And the reason is that the most valuable energy source of this century is fully wrong, fully outdated cost basis in their reports. And you see it here. This is a publication from this year from the major integrated assessment modeling teams. What are their cost assumptions for photovoltaic utility scale power plants up to 2050 in all major integrated assessment models? And in 2050, their cost assumptions are twice as high as today its reality in the world. And this is a major category 1 failure. It's not okay at all. So they assume $1,150 per kilowatt as average. The point is you can build in several countries, and really large countries today in the world, for 500 euros per kilowatt large-scale PV power plants. So they're wrong by a factor of 2 and 3 decades. If you then align it to 2050, then we talk on maybe a factor of 4. And this has to be corrected immediately. That's very important. By the way, this is IEA, so the projection of what is PV capacity added in the last 20 years of World Energy Outlook reports, and the black line is what had been really installed. So in every ordinary company you would fire the guys there. We know it has political reasons why it's different. But we really have to be aware that all technologies we use in scenarios are really on the most realistic value taken into account from financial and also from the technical constraints. Due to the time, I said everything, so this is the summary. It should be there. I'm still happy to take questions if possible. Many thanks for your attention.
Okay, now it works. I'm very glad that you started discussion on this energy efficiency impact of transition towards renewables, because that's a significant and not very well mentioned factor, but it's huge. I'm sure that Jiří would love this energy efficiency because he is the energy efficiency guy. Jiří, you will get the microphone from the other side. It's coming, it's coming.
It's coming. Thank you very much. I enjoy it because you are a lively presenter, which I fully support. I've got just one comment. I think the problem is not 100% rightly focused. Would save the planet 100% renewables? Well, it will contribute, but what we need to do, we need to reduce greenhouse gas footprints based on life cycle assessment. And renewables have got footprints, and some of them have got quite large. So I think the study should be about minimizing greenhouse gas footprints, and plus one issue which is based on behavior of people. You know, Denmark has got a very high percentage of renewables. And what happened last year? Greenhouse gas footprint went up. How it is possible? Well, people's behavior. Do you know about this Jeeves paradox? No, this is, we need to go to the sociology. When we've got a car, a new car, big innovation, which hasn't got 10 liters per 100 kilometers, but 5. What would be the consumption of the fuel? Would it be reduced to 50%? No. Why? Because we will drive more, you know, because we will spend less money. And in some cases, actually, the result is that people are consuming not 50%, but more than 100%. So we need to consider also the sociology and go for minimizing greenhouse gas footprints. Thank you.
Many thanks for the comment. Of course, we also couple the model more and more to what is the resource demand. The area you can calculate rather simply. So in the end, we talk on the fact that even 10 billion people in the world would live on such an energy system on that energetic level. We talk on roughly 1% of the global landmass needed for PV as the main source. And we learn more and more how to bring PV floating on water, currently maybe on land water, but the first projects and also publications go for offshore solutions. And maybe then the area demand is not so problematic. What I have not shown is the energy-water nexus, but this is great. If you see there are not any more much thermal processes, and in countries where we have a really water crisis, in particular also due to water withdrawals in rivers with thermal power plants, this really helps quite a lot to have then renewable electricity on that way. When it comes to life cycle analysis, we have to be very aware. If you take the standard databases on life cycle analysis, photovoltaic is typically wrong there. And the reason is they have 10 years old data, and then they do not get newer data from the manufacturers, which are mainly nowadays located in China. So this is very challenging. For cadmium tellurate PV, it's okay, because First Solar is collaborating, but the others are not so much collaborating. You have to be very careful. I saw once an article taking our data and then doing analysis on life cycle analysis for 2050, and they concluded, okay, we have a lot of negative emissions from PV, because they used the LCA data of PV as of today, which is then many years old, and assumed that will be still used in 2050. That we have to do better as a community, I guess we know. But I fully agree. I think what will be a major research topic in the future is, do we really need many plants and in particular many animals for food production? So power to food is currently starting in smaller communities where we can use bacteria to convert again water and air and electricity to proteins. And let's see, I guess there we can eliminate a huge footprint. But we do not yet know whether people will like these products. Let's see. That's research.
I'm very glad that you mentioned this LCA problem, because I think that the factors in LCA analysis should be calculated also endogenously in the models. Otherwise, using static values from the past is going to give completely wrong results.
Exactly.
Other questions? We had one here from Professor Kilkish. Are you still, the microphone is coming.
Thank you. This is Professor Kilkis from EU Renewable Heating and Cooling, RHC. I have two very short, time is short, and interconnected questions or comments. You mentioned rightfully that from the first law of thermodynamics point of view that the heat pump COP is around 3 or 4, and it contributes to the electric to heat conversion. But when we take it from the second law of thermodynamics point of view, electricity that you generate by renewables, all the renewables, the exergy of such a renewable energy or electricity is about 1 watt per watt, very high quality. You can do almost anything. But when you convert it to heat, especially below 100 degrees Celsius, like you mentioned, the exergy drops, and there is an inevitable exergy destruction, which also converts to additional carbon dioxide emissions. In order to be in line with the thermal exergy, the COP must be about 7. So until we get such technologies, electricity, renewable or not, must remain as electricity in allocating this energy source for different applications like industry, transportation, rather than converting to heat. And in this respect, solar PVTs. You didn't mention ever what the solar PVT is and why it's not in your models. Thank you.
Many thanks for the question.
Mechanical engineer, can you answer this question?
Yeah.
Yeah, you are. Okay.
I try to answer. So first of all, we have systems which start on pure exergy, because in the solution, when it comes electricity via heat pump to heat, this electricity had been from photovoltaic or for wind energy systems. So we start from pure exergy.
That's
From,
true.
from that point of view, we don't have the standard drop that we have to go down and back in the thermal
No.
process. It's the pure exergy here.
What I mean is, once you generate renewable electricity,
Yeah.
keep it as electricity for better use, not for heat. That's my point.
I
Yeah.
agree on that point.
No,
but
no.
what if you have excess of electricity which you cannot use for any other use? Why not use it for heating? So the whole concept of exergy works very well if you're using fossil fuels. But once you have variable renewables, power to heat makes sense because of the excess.
We are already one step further. If the power sector is fully fixed, everything in the power sector is 100% renewable electricity, but we still have greenhouse gas emissions from fossil fuel burning in the heat sector, then is the question, what is the least cost and best and most efficient solution in the heat sector? Then, of course, we come back to electricity. When it comes to PVT, I have been involved a lot in photovoltaic industry with PVT, so where we also use the thermal energy when we have the module, the photovoltaic module. On a module integration point of view, it seems to make sense, but we never found it for the last 20 years in the market. And the reason seems to be that separated systems, optimized, provide the energy service for a lower cost level. That is finally the reason why we don't find these technically working solutions really in the market.
We had a question there.
Okay, yeah, thank you very much for your presentation, and I agree, of course, that there are tremendous possibilities from renewables, but what we see also is, of course, in countries that have large endowments of fossil fuels, large reserves of fossil fuels, they expand the use of them much more than the expansion of renewables, in spite of that, as you correctly point out, that solar, for instance, is competitive to fossil fuels. So related to that, what would be your policy recommendation to get this tremendous disruptive change to come about?
Many thanks for this most important real-world question. So we had been asked 2.5 years ago to do a report for the G20 summit when it happened in Hamburg. What is the renewable energy policy, and also what is the options of the 20 leading economic powers in the world? And it's quite remarkable that today already several of these countries have the least cost energy supply based on renewables. Some are more or less at the edge, and for some the conventional option is still the lower cost option. This is data for around 2015. In 2030, there is, if a country would like to be an economic leading country in the world as a G20 country, the economy is based on renewable electricity because it's simply the economically least cost supply of the country. I know that was not exactly your question, coming back to those countries which have currently the resources in the fossil fuels. Then we see countries that perform very well with the transition and others not. Those which perform very well is an example like Norway, taking the value from the fossil business, putting it for the future generations and using it to find new solutions for new industrial applications to get, as a country, the transition done. And then we have other countries, they seem not to invest the value as of today in the maintained standards of living in the future. And there was, from my point of view, a most remarkable report early in the year from IRENA on the geopolitical impact of energy transition. This is really worth reading. There's only a few of these papers and reports. What is the impact? And of course, the present fossil fuel exporters in the world may have a really desperate situation if they use not the value, the fortune as of today to transition. Because many of them would have excellent resources. Just think in Middle East, also Russia, there are excellent renewable resources, excellent solar, perfect wind. I was once in Iran and talked to an advisor of the energy minister in Iran, and his question was, it was still the time when there was the opening of the country due to a different environment, and the question was what we should do. And then my immediate answer was, study in detail how Norway is doing it. This is a perfect role model. Also for such a country like Iran, they have excellent wind conditions, perfect solar conditions, excellent engineers, so they could be very leading in the power to X business, but it has to be active policies to really get the switch done.
There is a question there.
Okay, thank you very much for your interesting talk. My name is Mohammed from Brno University of Technology. Based on Energy Information Administration 2019, there is a prediction that in 2050, the amount of the energy will be like this. 4,000 pegajoule for petrol, for natural gas about 4,000, and for coal about 1.5, for renewable energy about 1,000 pegajoule. So, okay, this is one comment. The other comment is in management, we have something we call it weight value. And if we see about the renewable, how much is the value for this consumption, I can say it's below 8%, even maybe lower than this. So all of this, if it happens until 2050, we are, as a scientist, doing research and working for the area of below 8%. I would like to know about your suggestion and comment about this.
Many thanks for the question. We're indeed in a very desperate situation because the large majority of all energy we consume on this planet is from the wrong source and from the source that kills our civilization. That's a problem. And luckily we are not clever enough, but our kids are clever enough to be on the street to force all of us to do it, to get it done better and immediately. The good answer is the technical solutions we all have. From the what we need. From the economic point of view, it's available. However, where we are a bit, and I think corrupted is the best word, by vested interests. So there is a small share of people in the world who do outstanding profits with the destruction of this civilization. And I personally, as an individual person, do not accept that. So coming back, what you see here, so you did a quote for the Energy Information Administration in the US. Just see the numbers and the fossil shares. So some biofuels is allocated to fossil fuels. If that is the real scenario for the US, then the US will have very desperate economic times ahead if the rest of the planet is moving to other solutions. And of course this has nothing to do with a survival option. And we have this vested interest. There is an outstanding good report, I think it's now 2 months ago, from Banque Nationale de Paris, BNP, where they have compared for what amount of money you get what amount of energy back. So a kind of a ratio of money investment to energy return. And that's outstanding what you can learn there, what you get back from the fossil system, what you get from the renewable system. You get by factors more back from the renewable system than from the fossil system. In other words, the renewable system is economically much more performing. But this is not surprising, because there is a reason that the least cost source of electricity in the world is nowadays solar photovoltaics in most places in the world. So even if we have for standard market prices gas-fired power plants on a pure LCOE basis, they cannot compare or compete to that. Of course, we all know we have then to deliver the full 8,760 hours of a year. Due to that, we do it for full hourly resolution to find what is the best optimal solution. But the real truth is, if we really want to survive as a civilization, we have to move super fast to the real solutions. And this concerns us as citizens, as researchers, and also when we give policy advice. And practically all of us are here and they're asked for advices for companies and for governments. And then is really the question, what really helps us? What investments as of today are not stranded assets in 10 years' time, in 15 years' time? Because many of these energy investments have a technical lifetime of 20, 30, 40 years. And we know that from several countries that nowadays coal-fired power plants less than 10 years old are shut down. This is, of course, not the best economic performance. And if you follow the reports from Carbon Tracker Initiative, London-based, they have, with every report, with every year, higher numbers of the stranded asset potential of the global oil and gas industry. So that's really the question, how fast we can manage the change. But since we discuss all these topics now since 10, 20 years, I would say from now onwards, continued investments in the fossil infrastructure, if they are stranded in 10, 20 years, sorry, everyone knew it. This is no news anymore.
Well, according to International Monetary Fund, fossil fuels receive subsidies in the order of 5,200 billion US dollars per year. And now, because of the crash of prices of renewables, they will start crying for even more, I guess. But we have one last question before the lunch, and it's coming from, sorry, but the editor-in-chief of Renewable Sustainable Energy Reviews was the first one. You still have the question, Aoife? I do. Okay, microphone here, please.
Nice, finally, to meet you. You probably don't know me, or you probably know the journal, but you don't know me. And you know what? I'm exhausted from this. My back is sore. My head is exploding. Because do you know what? I'm a very practical person. And no disrespect, Nevin, when you talk about fossil fuels being subsidised, every industry in the world is subsidised. The aerospace industry, the pharmaceutical industry, the research industry, okay? So what makes me worried is that we have a situation where people are arguing about having 100% renewable energy or not. It's very disturbing to me as an engineer and as a practical person, because what happens is, if we go back in time, everybody thought the world was flat, yeah? Okay? We all thought the world was flat. And a few people said it was round, yeah? And they pillarized that person. They made that individual's life very, very difficult. And sometimes when you speak out against a large group of people, and I find it a little bit amazing, because do you know what? You're talking about 100% renewables energy. You're talking about coal plants. But yet, some of the people who talk about this are actually supported by the very industries that they actually give out about, which I find a little bit interesting. I'm not alarmist. I'm sorry now, Nevin. I'm sorry now, I have to say this. I think that there needs to be a bit of time from engineers and scientists. You can't electrify everything.
Yes, we can.
No, we can't.
But you will have...
no, we can't, Nevin.
You will have opportunity
and I'm
to
sorry
speak
now, leave me speak, Nevin.
On Friday,
I'm sorry, I want to say this.
We have to finish
if
the session.
If anybody's an engineer and they've built an overhead power line, they will tell you there's endemic losses in the power line. It's a fact, okay? Yes. It's the same with heat. You can't make something that's the optimum in what it is into something else.
Thank you.
I'm sorry.
We have to finish the answer, and do you think you can comment on this?
In the end, we have to look for a sustainable energy system which is least cost. And sustainable means that we don't consume too much of the natural resources, which means the ecosystems, which means the water resources, and which means when it comes to the emissions that we do not have greenhouse gases and something else. So we have to be on the best possible sustainable level. And then is the question what resources we have to match this. In principle, we can have biofuels, we can have heat, solar heat, geothermal heat, different forms of heat. We can have renewable electricity, but then society asks us to find the least cost solutions because someone has to pay for that. And that all we have to match. This is our task. And what is finally the least cost solution under all sustainability constraints and delivering finally the standards of living for all people in the world, because we should really realize we're all people in the world have the same rights, and also the next generations have the same rights, because this is sustainable development. For that we have to find the best optimized solution. And it has not to be the best optimized solution for a few people living here or a few people having here the most profits. And that we have to take into account, because this society requires from us. This will be my very general answer. And as scientists, we have to give advice to come as close as possible to this ideal world. We might be never there, but at least we should have the attempt to get close to it.
And the requirement, yes. And the requirement clearly comes from Paris Agreement, which all the countries now have ratified, even Russian Federation. So I would like to close this session now. Thank you, Christian.